Thank you, Jenny, for the introduction. I think I recall that Sarah from Dewey mentioned that she copied the slide from somebody and she felt bad. Now you should know how I feel when I stole the whole slide deck from my colleague. So Danny is behind all the work here, and I'm here just to pretend that I know everything, and hopefully I can answer all the questions. So how this performance benchmarking fits in EPRI's research. So EPRI is a nonprofit organization. We do like researches across solar life cycles. So we also have this so-called Solar Owners League. It's a user group for large-scale PV plants, and we do workshops. Like we just had July, we had a workshop for O&M, and then we have a website. We also have webcasts. We publish results, and we also do this so-called benchmarking. So the goal here was trying to, for our members, benchmarking their PV plant performance, all focused on large-scale PV plants. With mini metrics, they can play around. It's a website-based, so you can toggle, to see whatever you're interested in. You can compare to other plants. You can also compare within your plants. It's kind of based on the inverter level. So what I'm gonna talking today is, I think some similar theme you already saw. How to clean the data, the messy quality, all those kind of things, right? We have to deal with it. And then for the methods, we typically do 3 steps. One is normalization, and then we do the filtering, and then we do the trend analysis, and then show some preliminary results. We didn't finish all the work yet, still work in progress. So we have data based on 27 plants, 0.4 gigawatts, and we still have 35 to 40 to go. So it's based on the AC power at the inverter level. And then also with all the weather station data, the radiance, temperature, and range. And if somehow the data is missing, and then we will substitute with other data sources. We also added the incident angle from the PV lit, and also use some clear sky to estimate the irradiance. So the sampling rate is 1 to 5 minutes. This is the high resolution that we use for filtering a lot of outages and other issues. Now, in the future, there were a few things we want to improve. I think some people mentioned about using satellite data. We're going to try that as well. And also we're trying to also distinguish, for example, energy outage versus the data outage. We always see data outage as well. And then we're trying to automate the process better, and also using streaming data rather than right now is like a periodical, our members send us data, and then we analyze it. So first, data quality control. The biggest problem is the POA sensors. Since we're talking about large-scale PV plants, the maintenance of the sensors is always an issue. Right? So here's a few examples. Some sensors will drift away, and here shows one sensor, the blue one's kind of somehow drifting away. And then if you look at these, there's so many incidences that the sensor is not working. And if you look into it, and you can find out those kind of somehow it's stuck at some levels, it never gets to 0, and some are missing. And that's why you can have irregularity of really high and kind of irradiance or really low or something. So you have to dig into this and filter it out. Sounds like we are working on some process to automating this. That would be great. So And then, there's a few other things that we will also consider. I think I just heard about the daylight shifting kind of, fixes that will be also great. And then we also need to check the plan spec because, when you're calculating performance ratio, those kind of things that you making sure you have the right specification out there and units and consistency, all those kind of issues. All right, I mentioned about 3-step. I'll get into a little bit more detail on that 3-step. First is the normalization. We do a little bit different approach here for the PV plant modeling, and then to calculate the expected power, and then compare to the actual power, and you got your normalization. I'll get into a little bit more detail into it later. And then we do the filtering. We have 2 methods to filter the data. And then we will do the trend analysis. The metrics in the results we talk about today will be based on we consider the so-called healthy plant operation. That's like the normal state, non-clipping. So the clipping will be filtered, and the data will be also filtered data already. So normalization, right? The objective here is basically we trying to calculate the expected production based on the weather measured weather station data. You can imagine it's kind of like as a digital twin of a healthy plant. And then the data was trained on the first year of the plant on the inverter level. So you can debate on here, whether the first year is a good way, but so the goal here was trying to minimize some soiling and other noises. That's how we used it. And then this is 100% data-driven model. It's not like a PV6 and others. So what do we use basically is a regression model. So we did a study on different models, and we found actually the regression model actually predicts pretty well. That's why we, for the benchmarking, we're using the regression model. We also, added some, input variable transformations, like the incident angle and the log POA. And then we also added some second order polynomial expansions. And yes, so the model is trained on the linear region. You can see, so it's clipped here. Kristen explained what's clipping, and so we basically trained the model only on the linear region and excluded the clipping region. And so overall, I think the R squared is pretty good. So these are the 27 plants, and you can see the mean R squared is 0.95. And the median is 0.96. Now, some plants, for some plants, the R squared is much better than others. The worst one you can see here is, it's very hard to read here, but even I cannot read. It's about a 0.85, I think. So I did a study back then. So, but overall, like I said, the mean was pretty good. Okay, and then we for the performance loss rate analysis, we also use a clear sky model to kind of estimate the irradiance. Since there's so much sensor problems, that seems the biggest variation in large scale plants. So, however, right, you say hey, clear sky, well, that'll be much better. We found out it is better, but it's only slightly better, right? So the improved error was, kind of 10% versus 11% if you use all the data. And so it is a little bit improvement, but however, you also lose a lot of data. So the average clear sky duration is only 46%. So if you look at it here, right? In some plants, the clear sky duration, you can see it's only like 25%. So you will lose a lot of data for that plant. So that will be a concern. But anyway, so all the data presented for the performance loss rate was based on the clear sky irradiance. So two ways we do filtering. One way was we do the adjacent arrays. So for example, you can look at this, red curve, something's wrong compared to the adjacent array, which is a more like a normal situation. So then based on some, threshold, we will filter that. And then the other was basically a time threshold based, we came up with. So consider these are outlier and we just built it up. Trend analysis, basically the RD tool year-on-year kind of method was used here to reduce some noises, especially from seasoning and those kind of things. I think, I assume everybody here knows RD tool better than me here, so I'm not going into the detail on it. So here's our preliminary results. So regarding performance loss ratio, what we got was a median of 1.16 and a mean of 1.26. So that's based on the 1200, inverters. And so it's a little bit, worse than, from other reports. So if you look at for Enreal's 0.75 and from Lawrence was like 1%. So just could it be because we use a different method, but it could be also real. So we don't know basically, because this report says, different methods will produce always different results. So, and we didn't have the time to also dig into yet, which plan has a problem or those kind of things. There could be some problematic plans there. So this is kind of a breakdown of that 27 plans, and you can see some are performing better than others, right? Some are positive, some are negative. So it's even within one plan, you can see actually pretty very wide distribution, because everybody is like one inverter, right? So so it's kind of around 1 to 2% within a plant as well. We did a little bit of further analysis on it, basically compared to plant versus array to inverter to inverter, if you would say, right? So we take the middle 50% quantile of that plant, and then we plot a histogram on it and look at the mean. So within plant, you can see the mean is about 0.5, and then plant to plant is about 0.7. So they're a little bit, similar, but you can imagine because they should be different. They are different failure modes, right? So plant to plant is, more like global, since you are different plant, you could use different modules, all those kind of things. You have different climate, different soiling conditions, but then you can imagine within plant, it should be more similar, but they are also differences. There's especially, there's faults and failures, all those kinds of things happening in array to array will be different. And there's also individual module degradation will be different as well, or some of those things. So that causes some of the difference within plant. We also compared two different technologies. So here shows basically on the left graph was CAD-TEL versus crystalline. So you see CAD-TEL slightly better here, but there's no significance yet, right? So more data probably will tell later. And then this is about mounting. So checking comparing to fixed tilt. We also see fixed tilt seems slightly better, but also again, not enough data to tell it's significant yet. So we didn't try to explain yet, and this is basically an observation for now. So we did a little bit different way to calculate like a performance, right? So a lot of people use the performance ratio, and we use a different way. So we use basically our model, and then we calculate, basically normalize this to the so-called measured DC nameplate, basically translated to the standard test condition. what is measured. And then we minus to the listed DC plate, and then we calculate, we call it a system capacity loss. So it's a little bit weird here. Seems pretty linear. It's quite good, but then on the some high nameplate DC, somehow there's say some non-linear behavior here. Again, we didn't dig into it yet. We think it could be we got a wrong DC nameplate for some of the inverters, and so you got to test them. But overall, and then we plotted this as for the other plants, and we found the system capacity loss is about 12% for the mean and 10% for the median. You can kind of imagine this is like performance ratio. It's very similar if you do a 1 minus, so you're having about 90% of performance ratio. But we believe this is better because it does use a model, and also we take out the clipping. So for calculating this. All right, I think that's all about it. So the future works. A few things we wanted to do. First thing is we wanted to basically automate the process and then do more quality control on it. Then we also want to further reduce the model error, especially regarding the normalization stage. We wanted to try some non-linear regression models. I think we tried a random forest, and it seems it does reduce the errors, so we will try that. And we also wanted to add like a satellite data, and also adding some additional model inputs to improve the model. And then we also wanted to incorporate some decomposition algorithm for the trend analysis to basically consider the irregular performance, the soiling, seasonality and soiling issues. And for the website, right? So we wanted to add a more like user-specific views they are interested in. And also we are adding some additional filters. And of course, as I mentioned, we still have 35, 40 plants to go. And then we believe there will be more data coming as well. It's the 35 and 40 is based on what we already have. The data is already in F3, but then more will come and we'll add more data. And I think that's it. And thank you very much. Thanks for the attention.